So in this video, I'm going to look at Excel and how Excel performs in terms of running more advanced statistical techniques like ordinary least squares regression. So the reason why this is a concern is that at least since 1994, there have been statisticians who've looked at Excel and noted that it's not doing the sort of things that it's supposed to be doing. And in fact, early versions of Excel got multiple regression just completely wrong. Over the years, it's been fixed and tweaked and refined, but there still remain questions about how efficient Excel is and whether or not it really has precision out beyond about 3 decimal points, and how it works when we're talking about conditions where there's high multicollinearity. And multicollinearity is where you have multiple predictor variables, so independent variables that are actually correlated pretty highly with each other, and that can complicate the math a little bit and apparently creates issues for Excel's estimator. So the way that I investigated this is I ran an analysis of 50 countries and their corruption perception index values from the year 1996. And this is a replication model that I use for a lot of my examples. And you don't necessarily need to dig into the details of this other than to know that I ran the exact same model using Excel, R, SPSS, and Stata. So 3 common, widely respected statistical packages, and then also Excel. And we can look at how Excel performs against these other statistical packages across a couple of common indicators or details that we might want to focus on with regression models. So we'll start with the R-square values, and across all 4 software packages, the result was the exact same in terms of the R-square value. So in some models, it's rounded down to 3 decimal places, and other places it goes out further, but the result is always more or less the same, 0.8589, and that's across all 4 software packages. So that's good news for Excel and good news for our sense of confidence in how these software packages perform. When we look at the F-test, this is the overall test of whether or not our model is doing a good job explaining variation in our dependent variable. All 4 software packages produced basically the same results. 31.19 is the F-test, and the significance level, the p-value, comes in at very, very small, out to maybe 14 or 15 decimal points before you see any value other than 0. So again, very small p-values, and that's consistent across all models and all software packages. When we look at the coefficients, right, this is the numbers that we use to build our regression equation. Excel performs very well and matches SPSS and R and Stata across all of the various different coefficients. If you want to pause and really dig in and look and study, it goes out to multiple decimal points where it matches all across all different software packages. So this is helpful. It gives us a sense that whatever issues Excel may have had in terms of generating just outright wrong values for regression have been cleaned up. But that doesn't get at this other concern of whether or not Excel continues to perform well under conditions of high multicollinearity. And so I ran another set of models, a comparison of Excel versus Stata. And in this one, I basically doubled my independent variables. And so for each independent variable in my model, I added another independent variable that's similar. I call it, so with GDP per capita, I added a GDP per capita rand. And what that does is it takes the value that's there for that particular case and it multiplies it by itself, more or less, but randomly adjusted to be up to 5% above or 5% below the original value. And so the results are very, very similar. In fact, I ran correlations of the old values and the new variables, and they across the board have 0.99 correlation coefficients. And so they're very highly correlated, and there's a lot of them relative to the number of cases we have. So this is sort of our high stress environment, and we can compare and see how well Excel does when the deck is completely stacked against it and really stressing its estimator. So when we look at our R-square value, both models in Stata and Excel do very well. Stata has 0.8789. Excel produces something essentially identical. It just doesn't round it to 4 decimal points. When we look at the F test, again, both produce very comparable results. 14.967 or 97, and then p-values are again comparable. So again, overall model tests seem to match up across Excel versus Stata. When we get into the coefficients, we start to see this sort of break down a little bit. It's a fairly minor thing. So if you're just eyeballing this, you wouldn't immediately notice any real differences. Signs are all in the right direction. Even the first couple decimal points are all in the right direction. But I want to flag a couple things really quickly. So first of all, the intercept versus the constants, those seem to be sort of right where you'd expect them to be. Excel has a intercept or constant value of 12.212569. Stata is doing essentially the same thing, 12.21257. And so again, the rounding difference, but the results are more or less identical. I did find a place where the two models did diverge. And so with the economic freedom RAND, Excel is cranking out 0.317607, 0727, and Stata has 0.3176071, and so that 71 should be 72 according to Excel. Again, that's a pretty minor difference. We're out 6, 7, 8 decimal points before we see a difference, but it does seem like it is actually there occasionally under conditions of high stress. Okay, so what do we draw from these conclusions? What should this tell us? And I would take away from this that Excel is actually doing a really gosh darn good job. Certainly the concern that was put forward years ago that Excel was just getting it wrong isn't holding up. Excel is doing a remarkable job in terms of matching other statistical software under normal conditions and even under highly stressed conditions. It's matching up pretty well. It does seem, however, that concern that Excel might not be quite as precise when there's high multicollinearity holds up, that when you really stress Excel out in the 7, 8, 9 decimal points, it does start to deviate from what we see with other statistical packages. Now, is that a problem? And I would suggest, and I would put forward that I don't think it really is. And the reason for that is that when we're thinking about that level of precision, we're thinking about maybe p-values and standard errors and trying to figure out if something is statistically significant. Otherwise, at that level, we're not really seeing substantive differences. But when you think about your p-values and your standard errors, there are a lot of other things that are going to be relevant to that go above and beyond how precise your estimator is at 7, 8, 9, 10 decimal points, specifically dealing with issues of heteroscedasticity in our standard errors, right? And so programs like R and Stata have standard robust errors that are available to be added in and applied to models so that you can adjust for heteroscedasticity, so you can adjust for clustering, and that you can adjust your standard errors if you're using any sort of weighting mechanism. Excel just doesn't have those tools. And so if you're really concerned about having your standard errors right, you shouldn't be using Excel to begin with, right? Because there are other things that you'll want to be able to do that Excel just can't offer you. So under normal circumstances, if you're just trying to get a sense of patterns, I think Excel is certainly a valid tool to use, and you shouldn't worry that your coefficient results are going to be off compared to what you would see with other models. If you're doing a sort of sophisticated statistical analysis where you really want to be able to ensure that your standard errors are correct, you're going to need other tools anyway.